Good afternoon, guys. It's a pleasure to be here, here in Toronto with everyone. We're going to present our publication here, in which we touch in GPT-3, large language model, was the state of the art last year when this work has been performed. And we're going to present a two-step approach that we did, coupling information retrieval to add context to GPT-3 and do prompt engineering to get financial Q&A, which is question answering. So just introducing our team, we tell you guys a short story. We met at Stanford University during the artificial intelligence graduate certification. So myself, like my background is more into engineering, also business, and talking a little bit about Imran. Imran works for Google, developing LLMs for specific consumer use cases. And Mustafa has a PhD in finance, who I can say like pretty much he was the one who convinced us to do this sort of task in the finance domain. And we're going to begin first, like in the context, like we're going to begin with show you guys like a quick demo video with a high level real world application of this task. Then we're going to improve, we're going to show that, you know, that's pretty much the conclusion, that improving the context is key to achieve SOTA. Then some real world applications that has been developing since last year. We're going to touch on Bloomberg's GPT and some other papers. Then we're going to talk about other related work that we had at the time. I explain about a data set, and then dig into the approach, which is like the model is our system is a two-step approach. We first do information retrieval, and then we do prompt engineering in the large language model to show you guys the results and wrap up with the next steps. So this is like this video. In this video, I'm gonna quickly walk you guys through how you can prompt engineer a large language model such as GPT-3 and build very user-friendly web application such as this one, the Busy Bankers AI Wingman. So this app, what it does, the user pretty much loads up the file. Here we are talking about an Apple 10K financial report with hundreds of pages, right? So we're gonna upload the document. And the app already starts to ask you to prompt this document here, in which we're pretty much adding context to the model after instructing it with its role. And this is what we call prompt engineering part. So here we instruct the model in a string to run in every prompt, what it's its role, and some additional instructions to always translate the answer to English language, and if the query is out of scope, answer back with this default message out of scope. So let's start with a few examples here from Apple's 10K. So let's just ask, which page do I find the income statement? It's querying up the document. And it throws the answer here, gives out the answer in page 29. And here you have the chunk of text in page 29 from the document. Let's quickly cross-check this, opening this document. So here we have Apple's 10K. And the model answer, it was in page 29, right? So in page 29, let's just go for financial statements, page 28, and in page 29, consolidated statements of corporations, the income statement here. So the model was correct in this. You retrieve from page 29, as I'm highlighting here. Let's ask a few more questions. What were the net revenues from the last fiscal year? And net revenues last fiscal year 2020 were 274.5 billion. And it can do pretty much everything a large language model does in generative tasks, such as also translation. So let me just open up one last document about the Brazilian country that I'm from. Here we're talking about a paper company in cellulose from the name is Suzano. And let's prompt this document. Takes a little longer because it's a larger document compared to Apple's 10K, but here we have, which were the company's main market operations So the company's main market were the export of paper, the implementation of price increases in the domestic market, the acquisition of tissue, in the production plant at Mato Grosso do Sul, state of Brazilian state. Here we have the chunk of text. You can see everything in Portuguese, right? So it did the translation also coupled with retrieving information from the document and answering a question answering. So we believe this it has like a big potential to productivity gains in the finance industry. So guys, coming back from the video, now live. So we conclude that information retrieval was key to achieve state-of-the-art performance in the task, which is like finance question answering. So we ran several experiments with GPT-3, and we found that a separate retrieval model and a logic engine are essential components, right, to achieve SOTA. And especially because of the precise nature of the task, which involves like a complex analysis demanded from the model. So the nature of financial questions are like execute numerical reasoning pretty much, right? Also retrieve information from tables and from not only numerical, but also text into question answering to add as context to the model and do few shot in context engineering. And the financial queries are like very advanced analysis, which required experts in the field, highly specialized people from the finance industry. And the retriever must extract very critical details about the issue from the text. So some real world applications we've seen since last year. So Bloomberg released Bloomberg GPT, which is it's fine-tuned. It built up this whole model fine-tuning from a pre-trained GPT with a little bit distillation in a 50 billion parameters model, specializing in Bloomberg's proprietary data. There was Thin GPT, which pretty much combines several approaches, and it's more explanatory, this paper. And lastly, ChatGPT forecasting, pretty much stock price movements, and leveraging large language models to that task in the stock market. So in our related work, we had back then, last year, two strands of research. One was in open question answering, where researchers attempt to combine a high quality performance with computational efficiency, such as RoBERTa. RoBERTa a variation of BERT, more very effective and very efficient BERT architecture variation, which freezes like freezes the layers of the model, and through that adds on top of it additional layers to perform the information retrieval part, coming from documents. And in finance papers, they were mainly used in the domain-specific models to do sentiment analysis on the stock market. We saw many theme BERTs available back then. And here on the right of your screen, on the top right, it's an example we extracted from our paper, right? How the model does the information retrieval. The system, the entire approach does information retrieval, extracting information from tables and also chunk of text with also numbers, and performing math with it. So the data set, it consisted of a little bit more than 8K financial questions with answers. So it was labeled in two ways. First, pointing out here with the mouse, with program, right? So there was a question that asked for a numerical answer, and as a label, we could have as the first label the program, the model, the answer should actually conduct, right? So in this example, multiply the division of these two numbers in this constant, and perform this for humans simple math calculation, but for the model a little bit more complex, right? And as the other label was the straightforward answer, right? For each question, we had the formula, which is called the program, and also the final answer. We had two labels, and we're going to show the results we achieved here. So going back to our approach, the first step, it's a two-step approach, right? So we first retrieve information, and here we use a baseline BERT. So BERT is an encoder-only model for the transformer architecture, right? The transformer class, right? In which you pass in like semantics here for the input embeddings, like can you put position encoding just to be careful with the order of the sequence, right? I'm saying like here, for instance, like a sentence. And what is being very advantageous in the transformer architecture is like what we call attention, like self-attention, right? In which it visits and weights the semantics within the sentence, what is dependent and what is most important to be considered here in a prediction, which is like generating text, pretty much, right? And then we pass some normalization to avoid a little bit overfitting, right? This is like a regularization effect. And then we go to feed forward. And here in our approach, so we retrieve the information and we use using BERT, and we used as the baseline. And this is also an opportunity of improvement in the future, where we used where it was used like an LSTM decoder. So we reached a very near replicated the accuracy using BERT. But we can see there's still way to go to get to human expert level. But comparing to the general crowd, the system could perform better than the general crowd of the population. And we use as metrics accuracy with a given tolerance, which we believe it was also important to give some flexibility when the model predicted like with the wrong sign, for instance, but almost the same answer. So we give it some tolerance, and we're going to show later the results here. So that was the first step. So we add, like, this is like an example where we experimented in two ways, like with zero shot and few shot, right? So zero shot, like you only pass like the passage and the question and ask for the answer, right? As you can see the example here, which was the question was the growth rate in net revenue in 2003 for Energy Louisiana Inc. Sorry, company. So from the context, the model should answer like 5.5, right? Performing those steps. And we experimented also with few shot. Few shot, you give a little bit more examples. With zero shot, you just like ask and you expect for an answer, just providing the context, right? But here with prompt engineering, we did few shot. That's like in context prompt engineering. We did few shot prompt engineering here to predict actually the program, right? Given the program and predict what was the answer, right? So given the passage question, so here was like, what was the average cash flow from 2011 to 2013 millions? And the program, the model predicted the program, like to divide this, to perform this calculation here. For the sake of time, I'm not going to repeat here out loud. And we could see like comparing also to the gold answer, right? So we had the predicted program here. So in this table, you find like the question, a few examples of the question, like the predicted program, and what was the gold answer. And showing next, I'll elaborate here on the results we got. So we have here in this axis, like the accuracy tolerance, and if you increase, if you became a little bit more flexible, so if you increase this axis, can call it this elasticity, right? And here's the accuracy, right? So as I showed you guys, as adding like zero shot prompt engineering, the model did a terrible job. Like that's what we could find. Like, and it showed us that it needed that large language models fed with context and coupled with prompt engineering, they can do a fairly good job even to highly complex tasks, which is a very recent field right now. So when we release that, and we get to an accuracy of almost 80% here, as you can see. So what we found was like in the retriever, the supporting facts from the financial reports, concatenated with the question, and we trained the classifier using pre-trained large language models. In our study, we used the BERT as a retriever, and we're the program generator. So in the generator, we generate pretty much the top n retrieved facts. What we used here was top one and n equals 1. And then they serve as input to the generator. And here's, like you can see in the parameters, the configuration use a temperature of 0.1, the max token length of 64, text DaVinci -002, which was with the best performing model that OpenAI provided at the time. And also, as I said, like the top N is like top P, like equals 1. So as a result, you can see like the full passage context. The model, as I told you guys, it only performed correctly like 5% of the time with zero shot. But the SOTA is like near state of the art is near 60%. So when we relax a little bit on the tolerance, the answers pointed to that level of accuracy that we could find, right? In given retrieved passages, increased substantially the performance. And we kept increasing like with this approach, where we could find like accuracy with 20% tolerance to increase like from 60 to 65%, which is even seen like after Bloomberg GPT released its results, its initial results. At some tasks, some questions, some tasks, if you look at their distributions, we actually beat even Bloomberg GPT performance. So as an analysis, it's like we concluded that GPT-3 performs best when the retriever and the calculator are handled external to the model. So this will be like the correct approach here will be like to approach the problem with a end-to-end solution. Sort of like playing with Lego and assembling the parts here using our approach. So end-to-end, the experiments showed poor accuracy. It meant that the model was struggling to either retrieve the information about financial programs or perform calculations. In addition, here the retrieval experiments where execution accuracy increased 4 times. It strengthened the view that GPT-3 had the capability to do financial reasoning, but it struggles a little bit with to perform the retrieval part. So GPT-3's financial reason was strengthened when adding a specialized retriever model, such as BERT. we had some limitations during the when conducting this project. Computational resource, we ran everything through a consumer GPU, right? And Colab notebooks, which constrained us a little bit, if you not say a lot, right? And we acknowledge, like, I want to thank our families, and especially Stanford University Department of Computer Science to help us and guide us through this project. So as next steps, so what we're doing currently, we added the external calculator, right? Which substantially increases accuracy. The number of steps, which is an indication of that precision complexity in financial question answer requires a specialized retriever. And we're going to move forward with further large language models. So GPT-4 has been recently widely released to everyone. So we're already experimenting with this. Also, other large language models doing the same approach, but a better performing, larger model fed with more data. Also, opportunity, as I explained in the decoder part, using information retriever, not only with an LSTM, but maybe using a transformer decoder in the generator to compare results with GPT-3 here, or the large language model we use. And this could be all accomplished without any fine tuning. So we can still fine tune a large language model and probably reach better performance. So due to the limitations of the project, we couldn't fine tuning our LLMs. Can be very expensive. So we conducted everything within the constraints we had. And we believe we can contribute, building more finance data sets using this approach to build like this end-to-end task, and contribute to the field and also the industry. Yeah, thank you very much.